Okay, we're going to go ahead and get things started. All in the room, please rise. We'll get things started with the pledge as usual. If you're wearing a cover, please remove it and join me in the pledge. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. May be seated. Welcome to November 2025. Holy cow, where did this year go? Yeah. Let's see. First time visitors. I see anybody first time visitor haven't been to a meeting. Yeah. Yes, sir. What's your name, call sign, and whereabouts do you live? And your name? Michael? Fantastic. Glad to have you. Welcome. AA0EMD, you said? Fantastic. Welcome. Anybody else? Or brand new hams or license upgrades? How about online? Any first time visitors online? Nope. Okay. Fantastic. As always, if you know people who are interested in amateur radio, there are tests that happen, I think, every Saturday or almost every Saturday. Joe Ashley can help with information about that if you need to contact her, or you can email board@palomararc.org and we can get you connected to the right people. There are also ham classes for technician, general, and extra run by Jay Goldberg. San Diego ham classes, just Google that and you will find out when those upcoming events are happening. Let's see, repeater site and tech. Eeny, meeny, miny, who wants it? I see. No? Okay. Mark?
Sorry, I'm hiding up here. Not feeling real terrific tonight, although I do have another trip back up the mountain Sunday. Let's see. And Glenn, I guess, is a little puny too. Anyway, probably the major things are got the relay section wired up for controlling the flex remotely. Also set up some of the rest of the accounts, and we have local control of all of the computers on the mountain through a KVM switch now.
Nice.
So, Glenn, what am I missing? The next step on the tower is to erect the tower and get it vertically, absolutely vertical, so that we can grout the base in.
I think that about covers it.
All right.
Great. Anything else on modernization, or did that cover both efforts?
I think that covers both for now.
Okay.
Yep.
Good. Membership? No.
What?
He's pointing at you, Glenn.
You mean he's pointing at the screen? It could be any of us he's pointing at. Okay, I actually caught up on recording payments all the way back from in September, and I think that was about 15 payments, and so that brought us back up to 143 members. So we've had a couple more people that their memberships have expired since last month.
Lapsed. We don't say expired. We say lapsed.
Memberships, not members. It's subtle, I know. So if you have any questions about membership, look on the website. There's a membership page, and you can check your own membership by putting in your call sign. It'll say if you're current or when you expired, as long as you had your, not when you expired, when your membership lapsed, as long as it was less than about 2 years ago.
Okay.
So I got it. Thanks.
Great. Membership, of course, supports the repeaters being online and the power bills that keep going up on the mountain, and all the maintenance that we do on a regular basis. And this meeting, yes, the meeting hall is not free. We do have to pay for this. So, and the snacks, the donuts, and sometimes coffee. when Mark's feeling up to it. Okay, let's see. Upcoming announcements. Let's see. Oh yes, I need to talk about the auction last month was a huge success. I have all of the figures, and I do still owe some payments to the sellers. Those will come out this coming week. I don't have the exact figure in my brain. It was 960 something. It was in the scope. So if you go back and look at the scope, the proceeds for the club was 900 and change, and that is nearly double last year. So yeah, it was like combine the last 2 years together, it gave us this year. So that was a fantastic fundraiser for the club. Many thanks to our auctioneer who's back there dancing a dance in the back. Many things got rehomed to other garages, some of which I'm sure we'll see back at next year's auction. Some of which still need to make it to their homes. Mark, I'm looking at you who have the thing that I bought. That clock, when you get a chance. I forgot to remind you to bring that when you brought the food, the
Yeah,
picnic leftovers.
I put that and some stuff that Chris Baldwin wants all on top of the coffee pot,
Ah,
which is still sitting on top of the coffee pot.
fantastic. He'll come up for a cup of coffee. Okay. The slate for next, was someone gonna, oh, Chris, you were gonna announce the slate for next month for the election committee, right? Were you? It's the same as this year. So I can I don't have any data for this. Well, so shame on me. Or your um fearless leader who isn't here. So I have it right here in front of me. So if you want to come up here, and it's the president through director are the positions that are on the slate.
Okie dokie. Hello there. Okay, so the slate is as follows. These are the folks that are running. Okay, so your president, Joe, has said he'd like to continue. The abuse will go on. Chris, KD9LF's looking at a no? Nope. Okay. So we have an open position for VP then? Okay, all right. Looks like Jim Wasson's wanting to do treasurer again. Thanks very much, Jim. TQS for secretary, Ron AJ6FQ, and John W6XM for your directors. Am I seeing here that Glenn has stepped up for membership chair again? Okay, those are appointed positions. Got it. Okay. Got it. Okay. Well, I think that pretty much sums it up there. John S., Ron G. for your two directors, TQS for your secretary, and Jim Wasson for your treasurer. And there's an opening there for a VP. So good luck, Joe. We're all counting.
All right. Thanks, Chris. Okay. Upcoming programs and introduce the current program. Do we have upcoming program plans?
Oh, December.
Oh, yes.
December, the technical people of the club have forgotten what a big pain in the butt it was to do June. And as a result, pretty much everybody is willing to bring all their gear back and do it again in December. Hopefully it takes 6 months for the pain of the memories to fade. So I'll be bringing things like a precision 12-digit universal counter. You just key your radio in front of it and it'll give you the frequency to the nearest microhertz. I think it's actually only 100 microhertz. But that's probably close enough for anything we do. And I'll have a RF power meter. Of course, Chris will have all of his calibration equipment. Since mine is basically for laboratory use, he's only about 10 times faster at finding values than I am. We'll also have TDRs, spectrometers, you name it, just about anything. We can test power supplies. So spread the word. And I'm trying to open this to all of the clubs, not just PARC. So spread the word to everybody. I'm trying to bring all the ham radio clubs together. Did I leave
All right.
anything out, anyone?
Chris has his hand up.
It's really good time in December, so if you're thinking about coming out and on the fence, do it.
Yes.
Bring your gear, bring your friends' gear. It's a good time, and it's really good camaraderie and social time for.
Yeah, I know it's getting dark super early, but you know, if you can safely get out to the meeting, get out to the meeting and bring your friends, bring your gear, bring your friends' gear. As Chris just said, I'm just echoing that for those that are
Hey,
online.
Glenn, are you going to bring the spare repeater and show everybody how repeaters work and how digital repeaters work?
Yes, I will bring the spare repeater. It's a Yaesu, whatever is DRX1.
Something like that.
Yeah. Okay.
DR1X.
All right. Are there any video or audio in this? Oh, okay, go ahead.
What's being supplied and what's being asked to be brought?
As far as the equipment or food? Oh, yes. So are we doing, Mark, we're doing pizza and donuts and some sandwiches again, right? And then we're asking the members to bring something sweet, desserty. Oh yeah, no donuts.
Anything that will cause blood glucose to shoot up.
So the club will provide pizza and sandwiches, and everybody else brings something sweet. Diabetes, what? Are there any videos or audio in this presentation? Okay, I just need to know what to share. All right. All right, well, with that, we'll bring up Bruno, W4AFK. W4, right? I said 4. It says 4 right here. Okay. Oh, okay.
Hello. Okay, I think everybody's going to hear me. I talk loud enough anyhow.
Well,
Online? They hear me online, right? Okay, got it. Thank you. Hi, thanks. I'm going to do a short presentation on HF propagation. It's not going to be very deep. There'll be some technical stuff, but the whole idea of this is for you to, for new hams to get a better understanding of what's going on, and for other people to go and maybe do some research, dig into it, try to find out more about it. Because I've been doing this now since 1970. I also do this professionally because part of my work is we install systems around the world, HF, and high power systems and all that stuff. So this is part of the challenges we got to do always, essentially. So forward. So I've been a ham since 1970. I'm VE2EQ. That's my weird accent I have. I'm originally from Quebec. I'm American, but that's what it is. VE2EQ, W4AFK. Been a ham since 1970. I live in a condo. So I said, hey, how do I operate radio? Well, a friend of mine in Florida, we set up an HF station. We shared the price. If you want to see what it's like, just go to my QRZ page. I have 2 radios, amplifiers, multiple antennas, and I run everything from home. So, but the funny thing is that before I even turn it on, I check the city weather because there's so many thunderstorms there that when there's something within 5 or 6 miles, I don't turn anything on. So that's one of the funny things about that. So what I'm going to do is I'm going to talk about HF propagation, but it's not going to be deep. I'm not going to dig into many antennas, but I'll show you a few antennas you probably never saw before that are being used, that are being deployed, and explain what they're used for.
You can stay close to the microphone.
Wrong button. There we go. Sorry, thank you. I had a tendency of walking away. All right, I'm gonna stand next to the microphone. Okay, so for those, is there anybody here that is not on HF, that have never been on HF before? Oh, you've never been on HF before, okay. So I'm gonna skip through this pretty fast because this might be boring for you, because I thought there would be people here that are new, that are on VHF or that never played with it, but anyhow, so it's a good introduction. There's the radio spectrum. We're focusing on the HF part because that's the part that essentially is supported by ionosphere for global communications. You could do all sorts of weird stuff with the other frequency bands, but HF is the primary one that we're doing that essentially. So what's radio propagation? Pretty simple. It's a form of electromagnetic radiation like X-rays, light. It reflects, refracts, diffracts, scatters, absorbs. But the ionosphere is the primary enabler of long distance HF radio communications. So if you understand the basics of it, what to look for, you'll have a lot of fun with it essentially. If you don't understand it, you'll probably say the bands are bad, like today, for example. But one of my slides, you'll see what I mean by that. Everything's supposed to be closed, but I was making contacts with New Zealand. So there's nothing is perfect in amateur radio and HF communications. Now I say reflect and refract because people, okay, I'm going off the ionosphere, bouncing. Well, is it reflecting or refracting? I'll get to that afterwards. Okay, it has HF comms, there's a wide range of parameters, solar activity, different ionospheric layers, the signal geometry, the type of antenna you're using, the noise levels. All of these things contribute to HF communications, but once you have your system set up and you understand a few basic items, few basic parameters, you're gonna have a lot of fun, because then you'll be able to look at a report on propagation, say, oh, fine, I could operate in this band, it's gonna be open for me. Oh, there's too much noise here, let me go in a lower frequency. It's not that complicated once you understand a few basic principles above that, essentially. I'm also gonna talk a little bit about NIVIS, near vertical incident skywave, because that's very important for emergency communications essentially. And maybe all of you know about it here, but in my past experiences, many people didn't know about it, didn't know how to set it up properly to do NIVIS. Those are doing PARCs on the air. They probably are familiar with that because they're doing that type of communications essentially, but I'll explain to that. And the bottom line, I'm simply saying, what I'm trying to do is a simplified approach, because we could spend days just talking about propagation, how to analyze it. That's not the goal here. The goal here is to simply see some basic stuff, understand it, how to read the propagation, and then do your own research. And by the way, ChatGPT and these things, the new AI, it's unbelievable what they're capable of doing. You ask a question and it's pretty good. It's pretty cool. I would love when I was in college if I had that, but that didn't have computers back then. So, okay. What's special with HF? As you probably understand, we're able to communicate around the world with that. On the left-hand side, you'll see some of the stuff we'll be talking about. NIVIS, which is for local communications, Skywave, short skip, and that red area in the bottom where it says skip zone, blind zone, that's where NIVIS is important. If you don't know how to do that, then you'll not be able to talk to those people. And guess what? During emergency communications, that's what you got to do. You got to cover that range. You're not trying to provide communications to Seattle. You're trying to provide communications within our area, and that's the tough part about it, essentially. Okay, the modes of propagation that are out there. Evidently, we know VHF, UHF, HF. No, there's line of sight. Line of sight, yeah, I could use HF for that, but it's not very useful because I need big antennas, it's noisy, I need power. There's a lot of limitations with that to do line of sight, but it's a mode of communications. I could talk to somebody that's within ground wave or where I am essentially, but it's not really the best thing. Ground wave signals, essentially, that's different. I could go to the horizon over the ground, depending on the frequency you are at. It depends on ground conductivity. It's also best on lower frequencies. For example, the AM broadcast stations. That's what they're doing. And I'll explain the differences between day and night, essentially, what's happening there too. Skywave is what we as hams love for DX and communications, because that's how we go beyond line of sight, BLOS communications, where I'm able to bounce signals off the ionosphere and talk to all sorts of places around the world, hopefully. So a little bit of science again. What is the ionosphere? Well, up about at 50 miles, the sun has an impact with the upper atmosphere. It strips some atoms off the air molecules. The atmosphere becomes ionized, and that becomes a reflector. But I want you to think about something. If you ever put a glass of water and shine a light into it, and you notice that the light is, depending on how you shine the light or a little laser, you'll notice that it's going to change direction, essentially. That's refraction. This is what the ionosphere is doing. So it's going into it, the density is changing, and your signals, it's not going that and coming like that. It's actually going up. You're not seeing me here. That's true. It's making a curve up on top. Oh, it's Camry? Got it. So it's making a curve up on top and coming down. But we call it reflection because, it's pretty easy to say, but that's really what happens up on top. It's not like a flat mirror. And that's going to be a variable. So it'll bounce off, come back to Earth, and then how far it comes back depends on what frequency you use, what mode of propagation, what was the conditions of the sun, the ionosphere, which I'm going to explain. But that's the basic principle of that. The ionosphere is broken up into multiple layers. Again, I'll talk a little bit about them in the next slide, but on the right-hand side is the day side, and yeah, it's a little bit off-center, but just ignore that. But on the right-hand side is the day side. On the day side, you have F2, F1, E, and D. They're different layers that are there that are active. They're caused by the sun. The one that we don't like is the D layer, because the D layer absorbs all signals. If you listen, those that are familiar with AM radio, we all are old enough for that. Daytime, you hear local signals. Nighttime, you hear signals from multiple states and far away. Why? Nighttime, you notice there's no D ionosphere zone anymore. The D absorbs those low frequencies, so it doesn't propagate. Nighttime, it disappears. Next thing you know, you start hearing stations from Arizona, from everywhere around the country coming in on the AM broadcast band. Another thing that happens too is that the F1 and F2 layers up on top, they combine. So nighttime, you have a very good reflector in the ionosphere with the F1 and F2. And you also have the E layers, but that's why nighttime, in communications, that's the best time to do comms, essentially. We have the best propagation to play with. This is where, for example, when I operate from my Florida station, I've got a log periodic antenna, and I go from Florida to New Zealand at 100 watts, 500 watts, or 1,000 watts, depending on a signal. But I hear signals from Australia that I can't hear from here nighttime because the path is open, essentially, even when it says it's closed. Whoops. So the D layer, like I mentioned before, the D layer is the lowest one, and it really absorbs a lot of the signals. So like I indicated in here, it's present during daytime, it absorbs signals, it's signal attenuation, it's detrimental to HF propagation. Hams hate it, we don't like it. Broadcasters don't care. That's why they got to change their power levels and their intended directivity at nighttime, because essentially their signal goes much further now, essentially, than it was during the daytime. But it's there, we got to live with it. Why it's important is because if you're doing emergency communications and you're using NIVIS, you want to stay away from certain frequencies which are not going to propagate, essentially, because the signal will not go through the D layer. It'll be absorbed there, and especially at 160 meters. Chances that's going to happen. The E layer, the one above it, is a very funny one, because that one, if I stay with HF, is the one which is used mainly for NIVIS, near vertical incident. To do that, I got to transmit my signal upwards, straight up. The E layer will let you reflect the signal back down. So I'm going to show another slide afterwards, and you'll see what I mean by that, why that's an important one. But that's used to communicate, but E layer doesn't really support anything around above 20 megahertz. Now, when I mentioned that, we got to understand that's the rule of thumb. There's exceptions. You'll have VHF propagation going through E layers. You'll have all sorts of things that are going on, essentially, but the normal stuff is that it'll be, this is how it would operate. Sporadic E events, you got VHF running through there too, but those are exceptions. And I'll show you a slide where there's so many exceptions that you just, look, this is working. You didn't expect it to work, but it will essentially work out there. E layers doesn't support anything above 20 megahertz. Unless there's what they call sporadic E, it doesn't really want to work properly, because it won't support it, essentially, to refract it. The signal will go straight through it. And that's important, because if you want to do long range communications, you want to go through the E layer to go up to the F layers. If the E layer stopped everything, you wouldn't be able to do it, because the next ones are the F1 and F2. They're the highest ones. And those are the ones that we as hams use to do long range communications. That's the one that we want to play with. During the daytime, there's two different layers. Which one is the strongest depends on the solar cycle, ionization. There's a lot of things like that that affect it essentially. But we want to go to that layer, that end there too. It doesn't mean that signal can't bounce off E, but you want to go up to the F1 and F2. So, and those F1 and F2, that's 20 meters, 15 meters, 10 meters, 17 meters. That's where you're essentially, that's where you're playing your long range communications. And that's where it's doing it through those layers at that end. So this here simply gives a very quick, high level information as to what the layers do. There's a lot more details into that and to how it's ionized, what impact it has. But that's a generic situation for that. So frequencies, the D layer, it's about 50, 90 kilometers above us. It's really below 3 megahertz, but it's mostly absorbed. So, you know, during the daytime, it's not really useful. If you operate 80 meters daytime is pretty horrible. Well, it's because it's being absorbed. 160 daytime is pretty horrible too, because it's all being absorbed. The E layer is up between 90 and 120 kilometers. Daytime between 3 and 10 megahertz. That's the primary one you want to use for NIVIS communications, local communications. The next F1 and F2 layers are up in frequency, in altitude. But if you notice, the frequency-wise supported, the F1 is like 5 to 15 megahertz. F2 is 10 to 50. All that it's trying to say is that if you go up higher, you're gonna have better chance to go further away, essentially from communications, and it supports higher frequencies. And again, the F1 and F2, they merge during the nighttime. And with the F2, you can also reach above 50 megahertz. We had that recently during the solar maximum. We're in it now, but a couple of months ago, we had great DX on 6 meters. Very long distance, essentially. And so, well, how are you doing that? This is what was going on, part of it, essentially. You were getting, those layers were very conducive to reflect 50 megahertz and higher signals. The key propagation metrics, there's 3 of them. The 2 last ones, maximum usable frequency and the lowest usable frequency, is pretty simple. If I go above the maximum, there's no, the ionosphere will not refract your signal. It's going to be lost. If I go below it, it's not going to work either. So you got to stay between the maximum and the lower frequency. And I'll show you on the chart where you see that. The critical frequency, this is if you're doing NIVIS, that's going to tell you the critical frequency. When you transmit straight up, that'll reflect it down. If you go too high in frequency, it's going to go straight through and not come down. And if you're too low, it won't work. So if you're doing NIVIS, you want to look at that critical frequency to make sure that you stay within the range that my signal will be able to bounce and come back to where I am, essentially. Oh, I was going to say what happened here. Oh, I didn't put that animation, but it did it. Okay, the skip zone. What I wanted to explain here is if I got a few slides to talk about that, because that's important for emergency communications, and knowing how to set this up, it's very easy, and then you could provide comms. So what is a skip zone? The maximum range for ground wave it's the zone between the maximum ground wave and the first hop of the ionosphere. You're going to have an area where you're there, you won't hear anything because ground wave doesn't reach you, and the sky wave is going further away. So they'll hear 200 miles away, but nobody will hear you locally, essentially. So how do you cover that? This is where you want to cover NIVIS, which is called near vertical incident sky wave. And it goes, you know, for people that never did that before, they're saying, wait a minute, if I transmit straight up, it's supposed to go straight through. How come I'm able to use that to come down? That's the key, how to do it, what frequencies to use, and what angle to transmit up and down. So, and NIVIS is typically used up to about 10 megahertz. Above 10 megahertz, it's not supported. If you try to build a NIVIS antenna for 15 meters, for example, it'll never work because the signal is going to go straight through the ionosphere. It will never be refracted. So you've got to stay, typically the upper limit is about 10 megahertz. You could go to 11 or 12, but typically it's that. So you'll operate from 3 megahertz to about 10 megahertz, depending on the time of day and how it is. 40 meters is great for that, essentially, for NIVIS communications. 30 meters is good also, but 30 meters, essentially, you're not doing voice there. It's only data and Morse code. But 60 meters, 30 meters, and 80 meters, and 40 meters and 80 meters, as hams, we do that. In our world that we work with, essentially, we have all the frequencies in between that, so we could fine tune it and say, okay, this is now 8 megahertz, so we go and operate at 8 megahertz because we have frequencies in there too, but that's how it's played for NIVIS. Typical skip zones coverage. So on the right-hand side, it gives an example of the frequency range and the type of distances you're going to cover. So if I take 40 meters as an example, I could go up to 400 kilometers. If I do 60 meters, it could go from 0 to 400. Again, these are not absolute. So in other words, if my ground wave only does 30, 40 miles and I use NIVIS, I'll cover that and I'll be able to talk. And you might find it funny, but you don't need to have 10,000 watts to do it. You could do that with 20 watts, 30 watts, 100 watts. You don't need to have super high power to be able to do that, essentially, as long as you have the proper antenna and you know how to set it up essentially to get it done. So the chart on the right gives you examples of the frequency. I didn't go to other bands like 20 meters, 15, because they don't support NIVIS. So I just put those for that. On the right-hand side, it gives you an example of what's going on. The coverage area in the bottom is a skip zone. So I'm going up, I'm bouncing, I'm coming down, but there's a secret to that. And the secret essentially is that you want an antenna that has an opening of about 100 degrees. In other words, the beam width. And you want to aim it up between 60 and 70 degrees elevation. You want the pattern to go like that. That's going to give you the maximum coverage. If you go straight up and straight down, it'll work, but you want to give that type of coverage because if you think about where you're trying to go, you're still bouncing a signal. So as you're further towards the extreme, you might want to be going a little bit lower in angle or higher in angle to play with it essentially. But the funny thing about that is if you see, and what I wrote on top there, to install an antenna for that, you need to be close to the ground. I'm talking about for 80 meters, 10 to 20 feet above ground, and for 40 meters, 7 to 10 feet above ground. So you don't need to have like quarter wave up. As a matter of fact, you don't want that. You want it to be close to the ground to be able to reflect the signal back upwards. If you're somewhere where there's a bad ground, for example, in the desert, the secret there is you run a couple of wires below as a counterpoise to use that as an artificial ground to bounce a signal. I was in the Sahara and we were doing some comms and we were competing against another company had set up large antennas, beam antennas. They couldn't communicate with the capital where we were. And we went out there, we had a 20-watt man-pack radio. We set a wire up to a little tree brush that was sitting up there because there was no trees in the Sahara. And then we ran a couple of wires below it. We were talking to the capital solid. Everybody was coming over to say, how come you're doing that? They had high power in systems. Well, I didn't tell our competitor, but these guys were transmitting, they were hearing them in France, but they weren't hearing him. So in other words, they weren't doing it. So the key is understanding, okay, how do I do this? Proper height, how do I do it? What frequency to use? And it was working. They were all surprised that this little 20-watt radio, we were talking to the capital, but it's simply understanding the few basics, how to get it done, how to set it up to do it like that. So height above ground, those that are doing POTA and they want to do short range communications, they run a wire and it's not 100 feet up in the air. It's going to be pretty low and they're going to get that type of communications. But the key below you is understanding, do you have a good ground? If not, if you're on top of a wood building, the ground is not the building. The ground is wherever you have something else below it. So the key there is say, well, I don't have a good ground. I'll run a couple of wires below it to make an artificial ground connected to the ground line. That's part of the secret to get it done. And like I said, at the bottom here, like I indicated, it's useless to do NIVIS at 21 megahertz. It'll never work because the ionosphere it'll go straight through. So you might talk to aliens, maybe the spaceship that's running around, Tree A, whatever there. But yeah, that's it. Might be talking to him, but he won't be talking to anybody here, essentially, from that point of view. So this is just a summary of what I said. So in other words, the E layer supports NIVIS under certain conditions during daytime, most effective in the lower frequencies. Expect you could get coverage up to 250 miles, 400 kilometers. The F1 and 2 layers, you could have some NIVIS also, you got greater range, but that also depends on the density of it and depending on the condition the ionosphere in is at that time. E layers is going to operate almost every time. The F layer, not always, essentially. That's where you got to figure out how to get it to work. When we do E layer communications, because we have customers that need to do ground wave also. So we showed them how to do that, what to do, what frequencies to use. And because most of them are military, they could choose any frequency they want. You know, so they don't care. Hams. I've been in places where, okay, can we transmit here? Oh, you can transmit anywhere you want. Well, wait a minute. I'm allowed to do it? We're the law. Go anywhere you want. It's weird. Some places know how we do that. Okay, I was talking about propagation can be complex. I wanted to show this to say that, you know, we talked about the NIVIS, we talked about different modes, but it could be much more complicated than that. For example, if you look at the line number, I can go back there. It's going up, then it's bouncing between layers F1 and F2, then coming back down further away. So you kind of wonder, how did I get that coverage? I'm not supposed to be able to get it, but it'll work like that. Or you could go up, do an E bounce, come back down, it'll go back up and go F and go elsewhere. So there's a lot of complex ways. That's almost impossible to predict because it depends, you know, where it's going to bounce off the F2 layer. Where is that? It's going to be 500 miles or 1,000 miles away. Where is it going to be and what's the density of that place? So it's very hard to predict that. What you're doing in ham radio communications, even in professionally, you're telling what is the science behind it to get from point A to point B, what you need to do. How to set it up, what antennas to use, the power levels, how to get your signal the way you want to get it for data across the line. Special stuff like that you can project for it. I'll show you one at the end. It's a very special one that I'll be very surprised everybody heard of that one before, but essentially it could be very complicated. So this gives an idea of what could happen. And a lot of it is not standard, but you know what? You could have ducting. That ducting could bring you halfway around the world. Depending on, you know, how the ionosphere is. When there are solar storms, like during the daytime in a solar storm area, your area will be blanket, no communications at all. Go to the night side and the super communications. So it just depends. You got to understand what's going on with that. Have you guys ever, do you use this? Are you familiar with this? Do you know where this comes from? You know what that one? Okay, that's fantastic from the point of view of a tool. So this one here, this one was from October 11th. And October 11th, as you could see, we had good conditions, good propagation, was quiet, was pretty good. So if you look at what I look at when I look at this thing, I look at the solar flux number. And as I wrote in green there, if it's above 150, I've got excellent communication. I know I'm going to get very good propagation. If it's below 100, it's going to be limited, but you have, it's just not an absolute. The next thing I look at is the sunspot number. If it's over 100, fantastic. I'm going to get good. I know I'm going to get good propagation. If it's below that, it might be an issue. On the right-hand side, there's two of them called K index and A index. On this one here, if you look on top, the A index is 19 and the K says 2. I prefer looking at the A index because the A index is an average of the day. The K index is at 3-hour intervals. So you might look at the K index and it's going to say it's bad. Like in here, it says it's a 2. A 2 means it's excellent conditions. But if you look at the A index, it says 19. 19 says it's minor degradation. So over the day, you're going to have issues in propagation. But in the last 3-hour period, it was pretty good, essentially. So you get an idea. It gives you an idea of the condition during the daytime. I'll show you the next slide where very bad propagation with conditions. Here's this was October 2nd. You notice? Everything is poor, gone. No condition, everything's closed. Major storm. Noise level S6 to S9. So you turn the radio on, all you got is noise in the background. Look at the solar flux and solar numbers are nice, but look at the A index 54. And look at the K index 6. If you look on the right-hand side, 6, it's unsettled. And when you look at 54, it's a storm. At between 48 and 60, it becomes a major storm, essentially. So there was a major solar storm. The bands were completely closed. According to this, you say, hey, I got no propagation, no HF. That's it. I don't use the radio. Well, that evening, I turned the antenna towards New Zealand and I was making QSOs with them. I wasn't hearing anybody else from Europe, anywhere else. So I turned the antenna and I was in New Zealand and the stations, I was talking to them. So wait a minute, the band's supposed to be closed, but I'm talking to them. So the bottom line here is that if it's dead and don't hear you, then call the CQ. Who knows we're gonna pop up, because I was surprised to start talking to them at 100 watts and at 500 watts essentially, and I said, wow, according to this, the band was closed. So you can't always rely on that, but it's a good idea. So when I turn on my radio, I'm going to go do ham radio, and I see that, I go watch a TV or go do something else. I ignore it when I see that type of thing, because that means that it's going to be very noisy and pretty bad essentially. So on the right-hand side, it gives it as a summary of what the A and K indexes are telling you. And on the next slide, okay, the index, the other thing like here, QRN. What the previous slide here, it said between S1 and S2, which means the noise level was pretty low. This one here, now you've got a noise level was almost 10 dB, S9. So, you can't hear any weak signals. That's part of the challenging. Now, there's a lot of other parameters. If you look on the right-hand side, this is another one. This one was on another day, on the 13th. And it was active. We didn't have a major storm, but you notice it was saying fair. And the A index and K index are still high, but there was a storm being either we're finishing or starting, and the bands were now fair, which means you could make communications, but be prepared. It won't be wide open to talk to everybody. There's a bunch of other parameters in here, like the X-ray, 304A, PF, proton flux, electron flux. For ham radio, it's not really that important. But if you want to find out what it is, just use one of the AI search engines like Copilot or ChatGPT and ask it. I was surprised at how they provide the information in layman terms to understand it. And if you don't understand it, you say, please clarify. And they come back to you and give you that information. We don't typically use that in ham radio. Even professionally, we don't really use that. Those that do, that are professionals working on the HF field for propagation analysis and all that, they will look at all these parameters into here too. But if you start analyzing all of that, you need a complete training course to be able to get that done. We don't even do that ourselves. It's way too complex essentially to get that done. Now, I'm going to talk about this is an example from VOA Cap. I'm going to give you the links afterwards. There's tools online for you to check on propagation. They're free. You don't have to pay for them. This is VOA Cap. I went there. This is on October, conditions for October 2025 from Carlsbad, where I live in California, to Tokyo, Japan, using 100 watts with a dipole of 10 meters in height. And what should I expect for propagation? Information is there. And then VOA comes back and tells me, okay, for example, in here, highest reliability is going to be 20 meters between 6 and 1800 hours UTC, Zulu time, essentially. That's going to be my best chances. And if I want to operate earlier, like at 8 o'clock UTC time, they will say 10 meters. And on the right-hand side, you see they'll tell you what the chances are to get it done. So if you use a tool like that, plug it in, tell you what you want to do. It'll come back and it'll suggest to you and say, hey, you know what? Based on the conditions today, this is the best chance for you to reach Japan. Or if you want to reach Indonesia, here's the best time to reach it, or Kuala Lumpur, essentially, Malaysia, or around the world. It'll give you that information. This is the type of stuff that you look at. It's telling you the maximum usable frequency, MUF. So it's telling you can go, like for this one here, it's telling you you're not going to get, your best frequency is going to be around 19 megahertz. So if you go to 15 meters, 17 meters, 15 meters, sorry, if you go to, you have to 15 meters or 12 meters or 10, it might not work properly. You might not get good conditions because the best frequency is going to be around 19.8, which essentially is 17 meters if you want to play with it. So VOA Cap, if you go to that link up there at voacap.com, you could actually do your propagation study there. You punch in the information and it'll come back and tell you give you maps and tell you information how to do it. If you want to have it on your computer, running on the computer by itself, you go to the other link and you download it, install it on your computer, then it's hosted on your computer. And the last one at the bottom is from Australia. It's online, it's free, you could get it done from there too. The reason why I put that one there is us professionally, we used ASAP. They had a version of that, it was standalone. It was called Advanced Standalone Prediction Software. And we used that for like 15 years. They stopped making it available now, so we stopped using it. We liked that one because it gave us a lot of flexibility on the choice of antennas, the parameters, takeoff angles. So when we're doing a prop study professionally, it was helping us a lot. So they stopped offering it but they still do something on the online for free, and you could still do that there, but you don't have the same flexibility as when you have a standalone program. So there is a 3 sites, and it's all free. Could be a little bit of a learning curve when you install it because it's going to ask you a lot of parameters. But once you do it and you've done it a few times, it's pretty easy to be able to get it. You could use stuff like, you get reports like that. It also generates maps. If you have a directional antenna, you tell it what direction you want to point at. It's going to back power level. It's going to tell you what coverage it has. So it's going to be able to generate maps for that too. So the important things to look for: maximum usable frequency, lowest suitable frequency, critical frequency for the layer if you want to do NIVIS, the time of day, and the seasonal variations. My station in Florida, summertime, a lot of thunderstorms. And even if the thunderstorm is 60, 70 miles away, the noise is incredible, the static crashes. So, you know, if you want to do some good communications during the summertime, it's horrible because of that. Wintertime, a lot more fun because there's less static noise. We don't have that problem here, but on the East Coast, especially in Florida, every day there's a thunderstorm. So you look at that, how to work that out. Time of day, evidently, nighttime, daytime, it's different, and propagation also. Check real-time conditions, match band conditions, look at the solar flux, the K index and the A indexes. If the solar flux is low and the K index is high, use lower bands. If the solar flux is high and the K index is low, try the higher bands. These are basic things. So if you know that, that's enough to be able to start playing and having fun with it. If you want to do NIVIS, just make sure what the frequency is, typically between 2 and 10, stay below whatever. If it comes back and says the FO2 is at 8 megahertz, don't go above 8, stay below 8 megahertz. That's for because if you go above it, you won't get the signal being reflected back to Earth. For DX, use frequencies just below the MUF. So what you saw before is maximum usable frequency. That's a little secret too. Just if it says, like say, if it said 18.1, well, go one band below. Go below what it says there, a little bit below it, and it'll be better essentially to play with it. Consider, oh yeah, the other one is a gray line. You probably are familiar with that. Gray line propagation. When the sun sets, you've got great communications. If you follow the gray line from where you are across, you're going to be making communications that you never thought could be doable during that period of time when you have the gray line. Once the sun is set completely, you're no longer in the gray line. That condition drops. And when it's there, you're getting a mix of day and night propagation that's going on. And that's why you're getting some extra range to get it across. There's also beacon networks. I actually activate on WSPR net. I often have a beacon running from Florida and from here, where I transmit at less than 5 watts. And then it's reported around the world who hears my signal. So on our Palomar amateur radio station up on the HF radio on Palomar Mountain, I sometimes run the beacon at 5 watts. And I'm amazed with the web vertical. I'm heard in Australia, and Antarctica, and Europe, and Africa. So they come back and you get reports back saying, hey, I've heard the station. This is a single report I got from you. And so in other words, you know that, hey, the band is open towards those locations. Here's some tools. This is hardware now. On the left-hand side, it's called Quadra 4K. It costs $59. This is what's displayed on a 43-inch high definition 4K display I have at home. This changes dynamic. In other words, it's giving, that's a snapshot there, but those screens on top, it changes. It gives you other pieces of information that you want to track. Here I'm tracking the satellite ISS where it is. Those yellow lines here and orange lines, I had it looking for WSPR on a couple of bands. I had it looking on 20 meters and 40 meters. So it's telling me from where I am, it was reporting, hey, these are stations that are being heard at this location. So it's telling you, hey, the band is open towards Africa. It's open towards, South America. It gives you an idea what's going on at nighttime. If you're interested in this, the link is at the bottom. The owner of that site has terminal cancer. He's shutting down his business in December. I bought an extra one for anybody else, but essentially, if you're interested in that, it's not expensive. You better do it before he shuts it down completely because he can't produce the boxes anymore. It's a hardware box, plugs into your HDMI, plugs into your internet, and it's configurable. There's also a little keyboard that comes with it, so you could configure it, put your call sign, do your stuff. And it's gonna be able to tell you for propagation and even more details into that. On the right-hand side, much more expensive is the Geochron. I have that at home too. The Geochron is like $500, but it has a lot more. It has weather, earthquakes. Like in here, I'm monitoring earthquakes. At this time, there was a major earthquake here. I'm monitoring weather patterns. There was a hurricane, a cyclone here. ISS. I'm tracking multiple things. I see lightning strikes and all that. So that's also customizable. So it's giving you some ideas of different types of applications. I have that on my monitor, the same monitor essentially. I have it at home. So I could actually operate and actually see what I want to find out, propagation conditions and all that. So it's an interesting device, but it's expensive. I like the one on the left. It's cheap. And this one, you could build it yourself. You don't have to. I like theirs because it's 4K. It's a box. You plug and play. You want to play with a Raspberry Pi? The software is out there. You could take a Raspberry Pi, load the software, and you could have the same thing essentially. The $59 because I get a complete package. I just plug it in and I got a keyboard. I don't have to do anything else. I have Raspberry Pis. I don't want to do anymore. So I just said that's one to do it. Now, some odd antennas. Have you ever seen an antenna like that? Anybody knows what a spire cone is? Probably not. It's not really ham radio. These are some of the systems that we installed. It's an omnidirectional broadband conical antenna, covers from 2 to 30 megahertz. It handles 20 kilowatts, 40 kilowatt peak. It's the polarization is horizontal elliptical. It's elliptical polarization. I'll explain that on the next slide. There's a reason why that's being done. They're communicating to aircraft and to ships, and they want to minimize fading from polarization shifts. This thing covers both vertical and horizontal at the same time. So in other words, it's more immune to shifting of polarizations that's going out, which is very important for many customers essentially. It's multi-mode, so they could actually take the same antenna and switch it for Libis, long range, ground, ship to shore. It has 7 dBi gain. So it's a high gain omnidirectional antenna. This one here has an additional mast to be covered to go above the trees. We have this one installed too. This is a monster. If you look at the size of it, 208 feet, 87 feet, 110. The advantage of this one is this guy has 3 simultaneous 10 kilowatt transmitters. So I've got 3 transmitters feeding into this, and each one is 10 kilowatt and they're operating with no interference essentially. They're not transceivers. You don't want receivers there, but they're transmitters essentially. All of our systems that are high power, the receivers are many miles away. The transceiver sites, it's only a transceiver. The moment they have multiple radios, you never put the receiver there. So we got another site with tons of receivers. If you go to my QRZ page, you'll actually see at the end of it, sites where you have 4 10 kilowatt transmitters in one site, and you'll have receivers elsewhere and the different antennas that they're using. So this antenna, if you fly a commercial aircraft over Brazil, you're going to be talking to these systems because when they go over the Amazon, there's no VHF, UHF, and most companies don't use SATCOM. They're using HF. All of the comms are going through systems like this for HF. They're covering all the way towards the middle of the Atlantic, towards Africa, all the way down to Antarctica and up in the Caribbean. This is the territory that they have to monitor and operate and support all ground to air HF communications. So they have antennas like this for long range stuff. And because they have to be omnidirectional because they're not really sure where the aircraft is coming from. So HF comms is going to antennas like this or like that. You have some down there at airports, same thing too. They have these on airports and you see, when you look at that, say that looks like, man, why do they have that there? Well, again, they want to communicate to aircraft. They could switch to high angle or low angle, and then they could be able to communicate, reach the aircraft. Okay, technobabble, elliptical polarization. Who's familiar with that? Are you familiar with that and the line of work you're doing? First, okay. Surprised me. I thought that what you're doing at all that microwave stuff and the high level frequency stuff that something must be zapping. Okay. It improves ionospheric penetration. In other words, The summary is that I'm transmitting a signal in both vertical and horizontal. So as we know, if we transmit a vertical signal, once it goes through the ionosphere, you don't know how it's going to come back. It's going to come back, it's going to switch, it's going to bounce around, it could change polarization, go different ways. And we see that on VHF and UHF. You know, if you take a handheld antenna and you leave it like this, talk to a repeater, it's fine, do this, whoa, signal drops a lot. Well, it's not as bad on HF, but it's the same thing. You lose a lot of signal doing that. And for many companies or many customers, that's important that they maintain the best possible communications, even though when conditions become flaky like that. So they use elliptical polarizations, and that antenna is more immune to that. It's actually going to have both polarizations. Can hams do that? Absolutely. And some do it. Cross dipoles, cross horizontal dipoles, or loop antennas, you know, like the MSJs you sell. Put two of them like that, and you could do the same thing essentially. So they're hams do it. Some of them, they're doing it like the cross dipoles without really knowing that they're doing it, but that's what's going on. So improve ionospheric penetration, so it minimizes the distortion from the reflections. Resilience to multipath, again, on VHF, picket fencing, you know, your signal's bouncing off all sorts of buildings and coming back. It's attenuating or amplifying, and you don't hear anybody. You know, the signal's coming to you from different paths. Well, when you're doing elliptical polarization, it minimizes that, because now if one signal is coming like that and then one's coming like that, well, it's still going to be coming in properly. It's going to combine it and not say, oh, I'm going to give you 3 dB attenuation now if you're playing with it. Compatibility with different receiver orientations. Again, if you're transmitting with an horizontal antenna and the other guy in the aircraft is running, well, he's going to use a horizontal antenna that going up in the tail section, vertical, up in the tail section of commercial aircraft. And if you're running a horizontal one, you're going to have loss of signal. So what they do is that by using this type of antenna, they don't have that. You wind up getting the strong signal is pretty stable. There's conical monopoles. There are other type of antennas for long distance, but this is one of the favorite ones because it gives you gain. It's not just one unit gain; it has a gain to it also. And again, like I said, it's balanced. So, like I indicated before, cross dipoles 90 degrees with a phase shift side, and you could do the same thing too. And some ham have experimented with that. They've actually done that to say, hey, how does it work? But you know, it's one of those things you gotta be like Mark. You want to try and play, experiment with all sorts of stuff essentially to get it done. This is one I don't know if this is true. I was there in the jungle in Brazil, in the Amazon. They're in the Amazon. In the Amazon, you've got very dense jungle. They're trying to communicate beyond the horizon. They can't use satellite because the canopy is too high. That is blocking everything. Got to find a hole for satellite. They try to use HF. Doesn't want to work. The too dense foliage. So this is what they determined. This is what they found out, and it's science. It's true, and I saw them do it. They found out that if they use even 20 watts, if they run at 9 megahertz from the ground, they're going to get beyond the horizon, because what's happening is they're using the canopy and the ground as a waveguide. And guess what? At 9 megahertz, if you look at the height, you know, about 33 meters, if you look at what's going on at the minimum waveguide height, 17 meters, that's the canopy. So they actually figured out that, hey, I could use a manpack here, and I go beyond the horizon. I'm able to talk to them, and that they're using that. When I saw it, I was blasted away. You know, it was like, wow. Well, I didn't believe them, but then they showed it to me, and I said, congratulations, guys, you did it. One thing I learned about that one, evidently we can't do that here because we don't have any canopy, but they have it over there. So this is an interesting, you know, to show you all sorts of things that could be done with HF. You know, as hams, we have to do a lot of researching for frequencies, where we want to operate and all that. What's the best time to play with it? In the commercial and military world, they use what's called ALE, automatic link establishment, which takes away the black art of magic trying to figure it out. So these operators now become just operators. They push a button to say link with Chris, and the system will go out, find out the best frequency, link with Chris, and say, hey, your link, go do what you want to do now, especially for data transmissions where automatic. That what we've learned with that is people that used to be there that understood HF, there's less of them now. But you still need the people that how you program it. You got to program the ALE with the frequencies. You got to program the parameters into it. Once that's done, everything else is automatic. So some of our customers, they have people that program it, and the rest of it is, they're at a control center. These systems in Brazil, by the way, is all controlled from Rio de Janeiro, and they have transmitters everywhere around the country. And it's all being controlled from there essentially. So the people that there are operating remote stations, 5, 10 kilowatt stations spread across the country from a central location in Rio, essentially. The Navy does the same thing too. So they're using ALE to do the linking, not with aircraft, but they're doing a lot for ground communications. It's interesting concept. I like it. It's very capable, very powerful, but no, you still need people to be able to program those devices. And HF, at one point, we thought it was a dying hobby. It's not. It's actually, even the US government now, it's more and more interested in HF because they realize all of a sudden that the satellites we have are not that immune as they used to be. So, and many other countries are the same thing too. So we have a resurgence of requests for data, HF, but they're not they're asking for HF high-speed data. We have radios now that transmit, and hams won't like that, 48 kilohertz wide. We do high-speed wideband HF. It's a mil standard. We have our own frequencies. Okay. Oddly enough, by the way, we have some frequencies in the middle of 2 CV channels, and we're allowed to do that. We don't operate there, but we could wipe out the whole band if we wanted to with operating there. And believe it or not, we're authorized to do that in the middle of the 2-meter band. I have no idea how come the FCC gave it to us, but I could tell you something. Nobody does that because we're a bunch of hams in that company too. We will not do that, but we have a license to say, oh yeah, sure, you could transmit here, do your high-speed stuff and high-power stuff. But we don't do it. I never figured out why the FCC gave it to us, but we don't operate there. We don't touch that essentially. Yeah, our frequencies are not in the ham bands. They're far enough, but we have it across everywhere from like 2 all the way up to 30, and we go to 512 megahertz. We have a bunch of frequencies, and when we do operate, we could operate 5 kilowatt. We could do wideband HF. Our license at 48 kilohertz wide channels. We don't do it often, but we're capable of operating in those modes too. And that's where propagation becomes important. Yeah. Oh, Datron, where I work. What, sorry?
Your company has frequencies that have been assigned to.
Oh, yeah, we have HF frequencies, VHF, SHF. We have frequencies up into the gigahertz range. We have a bunch of experimental frequencies that are allocated to us. And we have 3 call signs that we operate under. And we're all to do secure communications, which we do some skunk work stuff. So secure comms, we do frequency hopping in the different bands. We do frequency hopping HF also, but we do it on the frequency bands we have. We're on a non-interference basis. So if I'm operating somewhere and there's another entity, we have to coordinate with them essentially regarding that. This is especially true up in the UHF range because there's a lot of users up there. So we're not primary, but we operate there. But on the HF side, we have allocated frequencies like Harris has theirs and Rody Schwartz has theirs, and we have ours essentially. So yeah, we have a whole bunch of. I'll show the call sign. You could do a search on the FCC. You'll see it. It's all there, and I'm the one that's responsible for renewing all those, all the paperwork we've got to do to get it done, and we got to do they last 2 years. Although the funny one is that the last one for HF they gave it to us for 5 years, which is weird because experimentals is supposed to be 2 years at a time. Whatever reason they gave us 5 years. Hey, am I to complain? No, we didn't complain. We took it 5 years of those frequencies. And what we do is we go for amendments. For example, the last time we renewed it, we had to add the 48 kilohertz wide because we're going to wideband HF. So we had to ask for amendments to be able to have authorized to operate on a wide chunk. And they go and check with the NTI. They go before they give us the license. They go and check with other users, whatever. And then we get it, and we're allowed to operate in those bands. So it's that and 80, it's 90. Yeah. Remember, a lot of the equipment we sell that goes out is it's military, and they don't care. Like I said before, if you go to another country, they say you operate anywhere you want. So it's a different story. But here in the U.S., we do sell a lot to the U.S. military, CCOM. We do a lot of business with that too, and we have secure stuff also that's being done. but essentially why we use the HF is to be able to do our testing over the air. We have a place, and we have lab, we do our tests there. We do range tests. A lot of times what we do for NIBIS, we drive people up to Borrego Springs. Or we go into the desert, and then because there's no line of sight, and then we're able to do testing from there to where we are. We are allowed, our license gives us 600 kilometers from where we are. We're allowed to operate. Here, in other words, to build operate. I could talk further away, but it means we actually have a station operate here. An example, we have another one in Texas. So if I wanted to work with Flex Radio, Flex is within our range, so I could tell Flex Radio, hey, you want to work with us? We're authorizing you to use our frequencies, and we could communicate between there and here because they're within the radius of where we have a set up in Texas also. So you have to have that because, you know, if you're designing HF, you got to have a way to test it. And we can't test it in ham bands because we're not allowed to use those modes. I can't do frequency hopping on HF, but I could do it when I have our frequencies to be able to play with it. So that's what it is. And I've been with this company for, in January will be 30 years. So my hair's white. So, and I spent a lot of time doing a lot of work around the world before I run engineering now, but before that, I was in sales engineering, and I was actually helping. We were configuring systems globally. In Taiwan, for example, I was the first forwarder to go into their in the mountain secure bunker center that we see on TVs, you know, where in case of a nuclear attack. I was the first forwarder to get into there, and everyone was looking at me, and I asked, well, why? Is it because I got white hair? And they said, no, you're the first one here. I said, am I allowed to be there? And they told me, you know, those two big, thick metal gates that we crossed, the doors that were open, the guards that were there, they have real bullets. So in other words, if I wasn't allowed to be there, I wouldn't be there essentially. So, but it's kind of funny because you look at that and say, well, these things we see in TV shows, yeah, it exists. You know, those that saw James Bond, you know, the suitcase. First time I saw one of those, because, you know, we work with Skunk Works and see that. Oh, wow. There's a catalog which you can't get. It's a catalog that thick. It's unbelievable. You want to buy a rocket propelled grenade. It's government. It's a catalog, you know, doing skunk operation. We don't do that, but we have drones, and some of our drones actually drop munitions. So, and we work with the government on that too. So, you know, we're in the drone business too, essentially. So, but it's all part of it essentially. I'm not involved with the drones thing except for the radio communications part, but I'm not involved with that part. Our people in Texas are handling that, but over here, we're doing the radio parts essentially for it. But but you know, we have it. Some of the stuff that's in Ukraine is some of our drones that are out there. It's funny because when they're one-time use, you know, quality control, just make sure it doesn't blow up. I always laughed and say, maybe one day they'll send us back pieces and say, hey, it's a warranty swap exchange. And all you get is a bunch of pieces essentially that something happened. But it's an enormous responsibility too, because you have lives of people involved, those that are handling it. You know, if you don't do the job right, and the person handling it blows up in his hand, there's a lot of responsibility there too. So, you know, there's a lot of checks and balances that we put into place, and the people that are doing that, you know, they got to be very careful. Now, HF propagation, what does that have to do with that? Well, believe it or not, when the drones, they wanted to do HF, and we had to explain to them, no, you can't do drones with HF. You know, you want to carry the antenna and power and all that. But it's a big struggle for them because it's a cat and mouse game. They find a way to get it across. It's now jammed. They find something else. It's now blocked. It's a cat and mouse game trying to get ahead. And they started talking about, let's do HF. I said, no. You need to understand this. You know, you want to pull up an amplifier and then put it in and transmit with that. That's when it worked. So getting back to this was interesting. I was blasted away then I did some research into science. It's true that it actually is supported by science, but if you never did it before, you say, are you nuts? What do you mean? How do you make the communications? And they're so proud to show that, hey, look what we're doing here. And they were doing that with 20 watts essentially. So that's essentially what I had, because like I said, the whole goal of this is just to give an introduction. I was hoping there would be people here that never did any HF to give some kind of a baseline. I hope I didn't put too many people to sleep that are familiar with HF, because, you know, this is read the baseline thing. The key is that this is going to be shared, I presume it's going to be shared on our website. If anybody wants to reach out to me, my email address is there, and I will help out and provide as much details as they want. I try to stay at the surface. So Glenn, Mark, did I bore you guys off? No? Oh, sorry. I'm seeing him here. That's why.
Oh, I'm
Because I talked to
sorry, I
this guy.
was asleep. What were you saying?
Yeah, that's what I was expecting to hear.
So I have a question. Oh, by the way, the one that we always used to use is it shouldn't blow up when it's not supposed to. And I was designing tactical nukes at the time.
Yeah, I wasn't. I'm not. Yeah, how should I say this? Good for you. I would not be interested in doing that.
So let me ask you, if it's the lowest frequencies we work with, why do they call it high frequencies?
Because it covers high frequency is what covers the 3 to 30 megahertz spectrum.
But that's
It-
the lowest frequencies.
No, you have low frequency that covers from 300 to 3 megahertz. You're making life difficult, right? Here, I'm going to go back to the first one.
You know, Bruno, if you didn't have
There.
one heckler in the crowd, what would you do?
If I what?
If you didn't have one heckler in the crowd, you wouldn't feel loved.
No, that's why I called you out. I know you. We work together.
Okay.
Yeah, sorry, go ahead. Yeah, but submarines, if you look at this chart. Okay, sorry. The question was regarding submarines, essentially what they're using and low frequencies, how they operate, what they're doing there. I know Mark will have his say on it, but I'm just going to say, if you look at the chart up here, you see VLF and LF, mainly VLF, and below that, that's where they're operating. And the reason for the wavelength is very long, and is able to penetrate the sea, and it's able to get long distances. But the lower you go in frequency, the less information you could send out. So typically, and again, correct me if I'm wrong, Mark, you were doing the nukes, but the subs essentially, they're going to get a very short message, like they'll get 3 or 4 letters. And then that tells them, open up your code book. Now you got to go here, go up to 10 meters, and then put this antenna up or do this or that. Or some of them actually have, they go to a certain spot, and there's a laser from a satellite coming down, a blue-green laser. It'll penetrate the ocean up to a certain depth, and they got to be a certain spot to receive the signal to be not interfered with. But the HF side, they can't transmit a lot of data, so it'll be like 3 or 4 letters, and that's to tell them, okay, open up your code book. You got to go and do this now, essentially. And then they go to frequencies where they could get more information to be able to play with it. So yeah, that's out in the VLF, and actually even below that, there's ELF, also extreme low frequencies, and they operate there too. And you got to get the wavelengths are, they're hundreds of kilometers for one wavelength, but you can't do a lot of data. So Mark, did I miss something?
No, actually, I think you covered that really well.
Thank you.
I went back in my day, which was back when my hair existed. It was ELF, and I
Yeah.
was just talking to someone recently, and they now have lasers that can go down to depth. But
What I
you
just
know,
said.
I know nothing about it. I find it amazing.
That's what I just said. That's what they do. It's a blue-green raised lasers, and the satellite's passing over a certain spot, and the submarine knows it's got to be there at a certain depth. He'll get a message coming down, a burst of information, and that tells him what he has to do essentially. And the advantage of that, it's almost impossible to intercept. You have to be there to intercept it. Radio comms, anybody like the ELF transmissions, anybody could pick it up. It's encoded, but they'll still pick it up. But this laser thing is different. It's there. It's not. You don't see it announced everywhere. We don't do that. We don't play in that area, but it's there. There's a lot of technologies out there we're not aware of that is being used now. So yeah, and what he said, ELF, that's below the VLF. You have that extreme low frequencies, and just look at what it says here. Look at the VLF side. The wavelength, one wavelength between 100 kilometers and 10 kilometers. So if you do a quarter wave antenna, go tell your HOA you're setting up an ELF antenna. Actually, what they do for ELF antennas, you'll laugh at this, they actually use the ground. They use the ground as a transmitter, as part of the antenna system, and they go out great distances, and there's a whole technique around that. If you want to find out more, just use ChatGPT and just say ELF submarine communications, you'll see what it comes out and tells you. But they actually use the ground because just imagine, you're not going to string 100-kilometer wire. And also, they're cranking a lot of power into this. They're going to put megawatts of power into it. So they're actually doing it to the ground. They have a ground screen, and they're using the ground as a radiator essentially. So it's a crazy thing. Now, important thing is that they're not receiving. These guys are only, their goal is to send a tactical information to the sub. That's all they're doing. They're not trying to listen what's coming back. They said, hey, calling all subs, here's your tactical message. Now from there, open your book, do what you need to do to go, and it could be go to a certain spot to get a SATCOM link, or what they also do is they stream out a wire in the back of the sub. There's a long wire. If they want to do LF communications, they string a wire that they pull out, and they use that as an antenna. And when the comms is finished, they pull it in. You're saying yes, are you a Navy or a sub guy? Okay, fine. Now, but the way you were saying, I thought maybe you were in the Navy doing that, because I know people out of okay, yeah, they string it out and pull it back in afterwards. You have aircraft that were doing that too. When the aircraft needs to talk to VLF, they'll do the same thing too. They'll actually string a wire, a cable out in the back of the plane. They're flying at a speed, so it's going to be out there. They do their comms and they reel it back in essentially, because if you look at that, trying to operate there, if you've got a 10-foot wire, how efficient is that going to be? If your wavelength is 10 kilometers and you've got a 10-foot wire, there's nothing being transmitted. So they pull the wire and pull it back in. There's all sorts of little tricks like that that are being done for those low frequencies. But
That's called a towed array. A towed array.
Sorry, oh, for that polarization, yeah, there is. You have that. When you compete with satellites, when you talk about satellite antennas, they're across. That's what they're doing. They're doing circular polarization. That's what they're doing. They talk about the right hand or left hand circular. That's what it is. It's elliptical. It's circular. What they're doing there is to reduce the fading. So you're going up. They say rotate that way, and coming down, it's rotating the other way. But so SATCOM, they're using that for ham radio use. No, because most of our repeaters are vertical. If you're doing DXing, they tell you buy out horizontal antenna. But if you're talking to repeaters, you want to have a vertical antenna. But if you want to talk to satellite, I say, well, your best bet is cross. You see these antennas, they're sold, they're like cross beams, and they point it up essentially. You could use a regular to the top, but if you have it cross the one, you'll have better performance because you'll be less immune to fading polarization because he's moving fast like that essentially. You're trying to track it. You've got enough trouble with a Doppler shift. You got to track the frequency moves. But on VHF, UHF, yeah, those are they're circular polarized. That's what they're doing. So that's why you have to cross dipoles essentially. But it's not really for talking, chatting, because there's no need for it. In Florida, I had friends that were doing DXing on 2 meters, and they have these long beams like PARC, EME stuff. You see these antennas that they're huge arrays of antennas, high power amplifiers, the bounce the signal off the moon. That's a hobby. You have to space it to do it. It's fun. It works. They do it. I've never done it, but I've been in places where they actually did it. EME, yeah. You can't start having, you don't chat. Hi, how are you? How's life? About that. You're doing CW most of the time, or Versal data, or some of the new data modes like G65, some of the new data modes, which facilitate that essentially. All they're trying to do is that, hey, I got a confirmation that they heard me in Paris, and I was transmitting from here, bouncing off of signal off the moon. That's what they're looking at. It's like FTD almost. You don't have a lot of effort to do, just let it get it done. In the past, before we had that, there's Morse code. You high-speed Morse code, you schedule. I'm going to be doing this now at 8:51 this time, whatever. Then they're both there. They bounce it off, both of them to see the moon, and it comes back down. There's a lot of weird things about that too, because the moon is not flat. What's called vibration. There's a lot of stuff when the signals bounced off, it's coming back in all sorts of polarizations, because when it's bouncing off the moon, it's not a flat surface. So it's all sorts of stuff that when it comes back. But you know, times to do it, they're happy like crazy. Wow, I just took my 20 array of 11 element beams and my 1,000-watt amplifier that just made it bounce off the moon. But no, it's a hobby, right? That's what we're trying to do. Yeah, I was thinking about that too. We could bounce signals off those of their metallites up there, the bones. Any other? Yes.
What counts as high speed in the context of HF, given its small? When we talk about the standard before we our counts, you're talking about how kilobits per second. Right. It's called mill standard 110D. And if you pull it out, 110 mill standard 110D is a delta. Have a look at it, you'll see it's called wide-banded HF. There's wide-banded LED, that's there too. You've got 24 kilohertz, 40 kilohertz. 9-foot slow scope is there. Otherwise, we're running a 6 kilohertz channel, 3 kilohertz channel. You're limited to these. We can't do much more. So they go off those. It's not a fantasy at all, because you've got to have 40 kilohertz wide available to do that. If you don't, the system cuts back to where you have continuous stream, and you don't just have 15 kilohertz wide, which means the speed is a little bit bad. Even that, it's still fast. It's not like VHF, you know, before that, you're running 100 or 90 kilometers per second, and the chip was fantastic. But now, the customers are looking for governments and developing. They want all they want now. They want a 90% clean. That's it. That's what they do. They want to find a propagation. You want to see that or not. They want to all be up on that, and they want to have a lot of data flow. It's a I could talk a lot about that, but there's a big debate, the European standard and our US standard. We need 48 kilohertz continuous. The European standard has 40 kilohertz and 3 kilohertz chunks. So they're spread out. So they're less immune, they're more immune to noise, but the processing power is enormous. Because now I got to go and take all these 2 kilohertz channels, which might be operating with different. I got to put them all together, take noise out and try to put it out. Which the advantage is that I don't have to look for 48 kilohertz continuous. Downside is a processing problem, a lot of times it costs more. On the US side, it's doing, but the challenge with the US standard is if you go to Africa or where you want to check, it's hard to find 40 kilohertz. You know, if you have a strong signal right in the middle, you can't use that. So that's the high speed stuff. I won't take too much time when you watch. No.
I got a message on how much.
I think we're trying to come. Hi.
Not trying to play that.
Any other questions?
Yeah, other questions.
Are there, the effect maybe to find them to be in real consideration? But you said that with you and your company, you work globally.
Yeah.
Have you noticed measurable or worthwhile still propagation on magnitude difference? Based on what where
Absolutely. People stations are near the equator. The propagation is different there because of the density of the atmosphere is always stronger because the sun, but where you're almost there. You also have transequatorial, so here in Florida, and when you communicate with South America, North South America, propagation is different because now you're going through a very dense area of the ice. So these are the things you got to look at. Where we are now, we're still far enough from that, and we don't know if we're going towards Asia or anywhere else. We don't have to worry about it. But they have to do that. So on the equator, around the equator, propagation is pretty good. Up north, it's the other way around. We have a lot of auroras. The auroras will affect propagation and destroy it. So it's very hard to kind of communications up north. I was at a military base to work just off the mountain of Pole. And years ago, I was up there on a project, and with fire with the Baytron in Canada. And there was something, it was still like John Cole, part of in the hole.
But no, the satellite antennas are all pointed towards the horizon, because that's where the satellite's gonna be down there. Then, there's an aurora, there's no. With the July and stuff that we used to have on board for the, protect that out of a very tough thing, we have to build a microwave link. Hundreds of repeater stations because they couldn't rely on them. They couldn't do the satellite back then, they couldn't do the channels, they built a series of repeaters to get the information back on, until we get to the spot where there could be something better. But out there, essentially, so that's bad up in the north, same thing in the south, in Antarctica. I think community station in Antarctica, Argentina, the research base, I also had contact, it's funny, I had contact once with VARCS, with an alert. And also Casey Poacher Blake, which was in Antarctica. I was there in both, they were giving each other, so I was there, and I was kind of talking, I was, hey, I thought you were talking to there. Can I relay any of that? Well, it was going to come with VARCS is no longer on the air, but when the word was that. But even today, in my WSPR 5 watts from Palomar Mountain, and I'm picked up at the guy from the gates, get back, if you're seeing on before, this is what about we do receiving meter transmission at 5 watts. So, propagation from, there's a solar storm, there's a bar to the north, but remember that also occurs in the south. So then the same thing occurs down there. So, yeah, so it is different, but so if you're working in that area of the world, like when I was in the Sahara, I had to focus on the fact in the desert, there's no good ground. What you do, what propagation you want, there's a lot of noise, static noise because the wind blowing the sand. So what are you going to operate? How are you going to do it to get it down there? Because it's going to be different than if you went up to Bulgaria on wood. So this is just a way. This is for here. We're in California, where we are. This is how we set up. In Canada, in the wintertime, snow. So there's a lot of stuff there too. You've got other impact now, but impact up here too. This is one we learned. They'll be curious to see what happens on the mountain of stuff.
Bruno,
Yes.
why don't you do just a tiny bit of advertising for the work that we're doing up on the site and let everybody know that you're going to demo it next month?
You just said it.
Well, what are you doing up there?
I know. I'm gonna step up now. All right. No, we're working on the HF station up there. We've had some challenges. The station is working. We're a few of us that are operating remote from home, and we're operating the HF station up there. It's a flex radio, flex 6400. We have a vertical antenna RA that covers 40 to 6 meters, and we have a wire antenna for 75 meters. We're testing it. We didn't open it up to everybody yet, because we want to have what he mentioned earlier about the remote control capabilities. We want to have that in place, because when we open it up, if somebody makes a mistake and accidentally the radio shuts down, nobody wants to drive up there to push a button. So this is what we're working on to make sure we're able to manage it, control it. Once that's there and we're able to do it, then it'll be announced by the club, and people will we're able to operate the station out there. It's a flex radio. So it's not, those that are familiar with flex radio or that type of a radio, it's going to be easy. My job is also to train people that are not that used to it. So I'll be with them at the same time on the air. So hopefully it'll be soon. The key thing is to have the remote capability in place. It's too easy to make a mistake and, for example, click shut down the computer in place of log off. Then you got to say, Mark, you want to drive up to the mountain and push a button. So, but he has that. We have that now in place. We figured it out. So we're going to do it. We don't have a front end for scheduling. I'm working with the Australian group, a ham club in Australia that are doing this. I'm working with them for them to share with us their code, their software that they're doing. But even if we don't have it, we're going to work on an honor process method. We're going to log it, make sure you have a license, and we'll work it out and get it done. We want to make it available to you guys. Ultimately, there's going to be the plan is to have a DB18 antenna. It's a stepper, high gain, rotatable antenna on top of the tower that they're putting up there. For now, we're using a vertical and a wire, but once that's going to be up there, you'll be able to access the system, the radio, control the rotator, control the antenna from your home. So that's going to be that's the whole goal for hams, and we got to train you how to do it. If we had a nice front end, it would be easier, but we don't have one. So we try to work what we do. But for now, it's a vertical, and it works.
You know, James is using it too, and we make contacts. I think James uses a lot, K6WRJ. He does a lot of data, FT8 and stuff. I do voice. I do a lot of other modes of operating, and it works, you know, and it's amazing. It's just a vertical antenna, but at 5,600 feet, it helps. There's one downside. There's a blind area behind us because I got a mountain. So I've got great coverage, but when you do a WSPR and look at the maps, who's listening, hearing you, you see all that. Then there's a V shape that way, very little signals. Huh. I was asking Mark if he's ready to blast a few holes in the back of us, but he didn't volunteer to do it essentially. Well, he plays with nukes, so I said maybe we did it
At one time.
at one time.
We thought our Wi-Fi got shut off at 9 o'clock.
Well, Mark and I were the only two talking to each other here for a couple of minutes.
Yeah. So I was saying to the people in the room here, no Zoom next month. I wish there were more people left on Zoom, but yeah, no Zoom for December. And in January, the Zoom link is going to change for reasons because Zoom is stupid. But it'll be advertised in the scope and reflected on the website, and I'll update the calendar event. So shouldn't be an issue for anybody unless they've got their own calendar event that they've saved this Zoom link, and it'll still be available for a bit. And if I see anybody join it, I'll hop on and say, hey, here's a new link. So anyways, 7-3 for now. Thank you, everybody, and have a great evening. Home safe for those in the room. Take donuts away with you for those in the room, and we'll see you next month. If those online that aren't coming next month in person, we'll see you in January. 7-3.